This is problem 457, and we're looking to obtain the Thevenin and Norton equivalent circuits. So the Thevenin and Norton, both of them, both Thevenin and Norton, between terminals A and B here. This problem's a little more difficult because we have a dependent voltage source, So let's start out with our first step where we turn off all independent sources. So this 50-volt source becomes a short circuit. And then we have our resistor, and we have here, and then our dependent voltage source or dependent current source, which is 0.5 Vx. And then we have a 10 ohm resistor, 10 ohm. And then we have our terminals A and B. So that is 2 ohms, 2 ohms. And this is 6 ohms. And that is the voltage Vx here. And then 3 ohms here. Okay. Now, for a dependent source in here, to find the Thevenin equivalent resistance, we need to apply a voltage source here. So we apply a voltage source of 1 volt between the terminals, and we're looking to find this current, the current coming out of that terminal, and by finding the current and having the voltage, we can then solve for the Thevenin resistance. Okay, so let's go ahead and start this problem. I think it's easy to see here that these two are in parallel. Those two are in parallel. So that is 6 times 3 divided by 6 plus 3. That's 18 divided by 9. 18 divided by 9, which is 2 ohms. 2 ohms there. So let's simplify the circuit. We have 2 ohms, 2 ohms. We have our dependent voltage source. This is 2 ohms, and this is 2 ohms. And as you see here, this is Vx, but we also have from here to here is also Vx. So Vx is here to here still. And I didn't write that very clear. This is 2 ohms. This is 2 ohms. And then we have our 10 ohm resistor here, and our terminals A and B with our 1 volt here, and we're looking for the current coming out of that 1 volt power supply. Okay, so where do we go from here? Well, I think you know that if this is 1 volt, we can call this down here our reference, 0 volts. That means this point and this point, those are both at 1 volt because of this, 1 volt here, 1 volt. Okay, so if we look at the current here that flows down here, we can do a voltage division, where Vx is equal to 2 divided by 2 plus 2 times this 1 volt here. So that means Vx is 0.5 volts, 0.5 volts. 0.5 volts here. Okay. All right. So if we know that this is 0.5 volts, then we know this current here. We know that current. So let's do KCL up here. KCL. And let's label some of these. We'll call this I1, and we'll call this I2. So in minus out. In minus out. Let's see. In minus out. So up here, coming in, we have I naught coming in. Going out, or we also have 0.5 times Vx, which we just found out is 0.5. Coming in, and going out, we have our 1 volt divided by 10 ohms. And our I1 going out, which is 1 volt divided by 4 ohms. 2 plus 2 is 4. So in minus out. And solving this equation, it looks like we have I naught equals, let me grab a calculator. 5.1 minus 0.25. It looks like that comes out to be 0.1 amps. So if we have this current that comes out of this, we can figure out our Thevenin, which is equal to the voltage source divided by I naught. So we have the voltage source is 1 volt divided by I naught, which is 0.1. And that comes out to be the Thevenin resistance is 10 ohms. So Thevenin resistance is 10 ohms. But we're not done yet. Let's continue on. So since we know the Thevenin resistance now, we turn back on all the independent sources, and we need to find the Thevenin voltage now. So let's draw this circuit. We have our 50 volt voltage source, resistor here, and we have a resistor up here, and then our dependent current source, and another resistor over here. And these are our terminals here that we're trying to find. This is 6 ohms, and we're trying to find Vx here, and 3 ohms here, 50 volts, and 2 ohms here, and this is 0.5 Vx, and then 10 ohms. Okay, so let's solve this problem, and let's do our mesh analysis to solve this problem. So I'm going to draw, we'll call this I1 and I2, and lastly I3. So let's do our mesh analysis, and starting here, that is negative 50 plus 3 times I1 plus 6 times I1 minus I2 equals 0. Okay, so expanding that out, that looks like it's 50 plus 9I1 minus 6I2 equals 0. And that will be our first equation. Now, since we have this dependent source here, let's go around the outside here. Let's go around the outside. So we'll start here, and then we move up this way, and that is 6 times I2 minus I1. And then here we have our plus 2I2. And then we're going to move over here and then down. And that is plus 10I3 is equal to 0 here. Okay. So we need one more equation here. And we have one more, which means I3 minus I2 is equal to 0.5 Vx. And we have another equation here, which is, we know that, let's see, that is I1, well, that's 6 times I1 minus I2 is equal to Vx here. Okay, so let's plug this value in here first. We have I3 minus I2 is equal to 3I1 minus 3I2. And taking a look, let's move I2 over here. We have I3 is equal to 3I1 minus 2I2. Okay, so that can be our third equation. And let's put that in up here. So we have 6I2 minus 6I1 plus 2I2 plus 30I1 minus 20I2 equals 0. Okay, so let's combine some terms. That's 8I2 minus 20, that's negative 12I2. And then we have plus 24I1 equals 0. And we get I2 is equal to 2I1. I2 is equal to 2I1. And then we use the last equation up there. We have negative 50 plus 9I1 minus, put this in here, minus 12I2 or I1 equals 0. So I1 is equal to 50, negative 50 divided by 3 amps, which then I2 is equal to negative 100 divided by 3 amps. And then I3 is equal to 3 times negative 50 divided by 3 minus 2 times negative 100 divided by 3. I3 equals 16.6, which is 50 divided by 3. 50 divided by positive 50 divided by 3. So I3 is 50 divided by 3 amps. Okay, so we know I3 is 50 divided by 3 amps here. So the Thevenin voltage. The Thevenin voltage is then 50 divided by 3 times 10 ohms, which then comes out to be 500 divided by 3 volts, which is also equal to 166.67 volts. So we have the Thevenin resistance up here, and we have the Thevenin voltage now. So now that we have the Thevenin voltage and Thevenin resistance, this problem wants us to find the Norton equivalent. And if you remember, the Thevenin resistance is equal to the Norton resistance, which is 10 ohms. So we don't need to solve for the Norton resistance, but we do need the Norton current. And I'll show you how to solve this. So we draw the circuit, we turn the independent sources back on. So we have 50 volts and 3 ohms, 6 ohms. And so this is 3 ohms, this is 6 ohms, and this is Vx here. And then this is 2 ohms. And then we have a dependent current source, which is 0.5 Vx. And lastly, we have this 10 ohm resistor, and we have our terminals. Now, when we do the Norton, we short the terminals and we look for this current here. We look for this current. And if we do that, you see here that this is connected here. So the current going down through this, the current is 0. Because this is connected here. So we can just eliminate this resistor here. I'll eliminate that resistor. And so then we just have this equation to solve. Okay. So let's do a source transformation first here. And remember, we have Vs equals Is times R. That's 50 volts equals Is times our resistance, which is 3, which makes our source equal to 50 divided by 3 amps. So moving down here, we have a, let's see, let's redraw this circuit. We have 50 divided by 3, and that is in parallel now with the 3 ohm resistor, which is in parallel with the 6 ohm resistor. And this is Vx here, across here. And then we have our dependent current source, which is 0.5 Vx. And then we have our Norton current that we're trying to find. So these two are in parallel with each other. So we have 3 times 6 divided by 3 plus 6. That is 18 over 9, which is 2. So we have 2 there. And so I'm just going to erase this. And draw in our resistor that is now 2. I guess I forgot this resistor. We need to have that resistor in there. So that is 2 ohms here, and this is 2 ohms here. And so that's Vx. And here we can, let's do our nodal analysis here. Our nodal analysis. So coming in, we have 50 divided by 3 coming in, and we'll say this is going out and this is going out. So this voltage is Vx, and this voltage, if we set this here, this voltage over here is 0 because it's all connected here. So going out, we have Vx divided by 2, and then we have minus this, which is Vx divided by 2. And we set that equal to 0. And solving, we have, let's see, what is Vx? Vx is equal to 50 divided by 3 volts. 50 divided by 3. So, that makes this current here 25 divided by 3. So let's draw our circuit. We have 50 divided by 3. And have here. And this current is now 25 divided by 3. And we know that this current is equal to Vx divided by 2. That's 25 divided by 3. And we have our short circuit over here, our Norton. And so this must be 25 divided by 3. And so coming this way, we have 25 divided by 3 plus 25 divided by 3. That means IN is equal to 50 divided by 3 amps. So that is our Norton current. Now, going through this problem to solve for this, we can do that and solve for the Norton current. But you can also take into account that the voltage Thevenin is equal to the Norton current times the Thevenin resistance, which is also equal to the Norton current times the Norton resistance. So we could use this relationship, and we had the Thevenin resistance, which was 500 divided by 3, and we knew that this was 10. We could have just solved IN is equal to 50 divided by 3 amps. And that would have solved. These two are equal.